Hello, my name is Caleb Massengill, and today I'll be presenting a systematic framework to generate invariants for anomaly detection in industrial control systems. This paper was presented by Cheng Feng at NDSS Symposium 2019. In this section, I will introduce the concept of invariance as an alternative basis for detecting ICS anomalies. Invariants are unchanging truths about the operation of a system, such as safety interlocks or physical limitations. By monitoring these invariant conditions, we can more effectively identify deviations from the fundamental rules of a process. Traditional anomaly detections typically rely on models that predict sensor readings and raise alarms on large prediction errors. However, ICS sensor data is noisy and thresholds are difficult to tune. This allows for clever and patient attackers to make slow and gradual changes to fly under the radar of traditional threshold-based anomaly detections. The proposed approach, when properly implemented, can provide more robust detection capabilities. If an attacker induces a state that breaks an invariant, we should be alerted immediately without the need for thresholds that are typically used. I've included a diagram from the paper on this slide for reference. Here's an example of an invariant rule that could be utilized in this control system. I'll reference MV101, which is a motorized valve, as valve A. Valve A here fills tank T1. And I'll reference W_INT as flow B, as it is the flow rate from water between this valve and tank T1. As an example, if valve A is open, or when it opens rather, the flow for flow B must increase. This is only one example, but the same concept can be applied to other parts of this control system as well. Using invariants in this way allows us to leverage the ICS's own physical laws and design constraints and use them as alarms. While this example may seem simple and insignificant, the same logic can be applied to any control system. Imagine a boiler system at a coal power plant. Part of this system is controlling and containing ammonia gas, which is deadly to humans. Failure to detect malicious anomalies in systems like these can pose serious risk to human safety. This section explains why a manual approach to invariant creation is inadequate for modern industrial control systems. First, defining invariants by hand is labor-intensive, costly, slow, and generally ineffective. Industrial systems are often extremely complex, and manually defining all conditions that must hold would take significant effort and flawless process documentation. As I continue with my presentation, I'd like you to ponder this question. How many rules can a human realistically define in a control system? Typically, it's far fewer than the total amount of rules needed to cover all normal operating conditions. Even after investing that effort, the resulting rule set would likely be incomplete due to the high likelihood of missing relationships that weren't as obvious or well documented. Large control systems have hundreds of sensors and actuators, which, more often than not, results in engineers only specifying a small subset of all possible invariants. Building on my previous coal power generation example, if the relationship between the pump that adds ammonia into the boiler and the fan that keeps a vacuum on that boiler is not well documented, there may not be an invariant rule created for it. This could result in a situation where the controller of the vacuum fan has a failure, but ammonia continues pumping into the boiler, which can have catastrophic effects. Moreover, manually written rules can often diverge from reality. The industrial control system might be operated in ways that the designers didn't fully anticipate, meaning some handcrafted invariants may be too strict or even entirely incorrect. This can cause false positives or worse, false negatives, or the failure to detect real issues. Another issue is that manual invariant rules tend to focus on one subsystem at a time. Complex attack scenarios typically exploit several subsystems, And those cross connections are exactly what manual rules tend to overlook. Finally, industrial control systems are not static. Any changes made to the control logic or the process itself could render certain invariants invalid, requiring continuous upkeep. These challenges set the stage for an automated solution that can learn invariants from data, which reduces reliance on exhaustive human input. Continuing on, I will now explain the proposed framework. The goal of this framework is to automatically discover and create invariant rules from historical ICS data logging to determine normal operation and leverage inherent control logic in the data instead of relying on manual design knowledge. The approach involves a combination of machine learning and data mining techniques to systematically derive rules. The framework uses ICS domain insights, but no prior attack data. The key steps of this framework are as follows. 1. Create basic condition statements, predicates from ICS data. 2. Treat these predicates as building blocks and find consistent patterns that always occur together during normal operation, then turn those patterns into invariant rules. And 3. Ensure the mined rules are statistically significant or not coincidental, and remove any redundant rules. This results in a set of meaningful invariant rules that are ready for deployment in anomaly detection. The proposed framework uses two data-driven methods. The distribution-driven strategy observes sensor value distributions to infer operating states by clustering sensor updates into Gaussian mixture models, or GMMs. With this strategy, we're effectively discovering the different modes or operating conditions of each sensor. For example, if a tank level sensor behaves differently when pumps are on versus when they are off, the clustering will naturally separate those modes and create predicates for them. The predicate could be tank level change is in mode A versus mode B. These predicates then become conditions, like tank level increase is small for mode A, which could correspond to pump off, and so on. Using GMMs in this way helps choose the correct number of modes automatically. The event-driven strategy determines what actually happens when actuators change by observing sensor responses to process events. Essentially, it asks which sensors reliably respond and in what way. By fitting a linear model, it finds predictable relationships in the system. If the relationship holds true each time in training, it becomes a rule. This is achieved through simple linear regression, which is both efficient and easy to interpret. Its use results in many small rules or predicates. This slide focuses on the phase where the system actually derives invariant rules from observed ICS behavior using structured predicates extracted from log data. The process starts with item set creation, where system states such as sensor readings, valve positions, and actuator statuses are grouped into categories. For example, a condition might be pump P101 is on, or sensor AIT202 is greater than 5.0. These simplified logical conditions are predicates. Once we have these predicates, the next step is frequent item set mining. This involves finding combinations of conditions that appear together often during normal system operation. The assumption is that if two or more conditions frequently occur in tandem, they likely represent part of a stable expected behavior. This is an invariant. From these frequent patterns, the system can derive invariant rules. These rules are filtered down to only the meaningful invariants, or invariants that consistently hold true and have strong historical data to support them. The diagram to the right shows how this logic applies to a real-world ICS. In this case, a water distribution system. Each component, like reservoirs, pumps, and dosing stations, is associated with sets of these predicates. The system looks for consistent co-occurrence patterns, which it then turns into rules like if valve MV007 is open and the P2A sampling station is active, then pressure at PIC003 must be in range. These kinds of rules are the backbone of anomaly detection when utilizing this approach, and the fact that they are mined automatically from system behavior makes the method scalable and less reliant on manual engineering. This slide covers the next step, parameter tuning. This step is often overlooked and underappreciated, but it is absolutely critical to the success of the invariant mining framework. The quality of clustering, which is the foundation of later feature selection and rule generation, is highly sensitive to parameters like the number of clusters or distance thresholds. Poorly chosen values can group unrelated system states together, producing weak or misleading rules. Similarly, during rule generation, tuning thresholds for rule support or confidence affects how specific or general the invariance will be. If they are too strict, you will miss valid behaviors. If they're too loose, you will generate noisy or overly permissive rules. There's also a practical trade-off to manage. Tuning for higher precision may reduce the number of true positives you catch, while tuning for more general coverage can produce lots of false alarms. In practice, this often involves a combination of empirical testing and domain expertise, or more specifically, the understanding of what system behaviors should be grouped together and what conditions are meaningful for safety or stability. The bottom line is this: without proper tuning, even the most sophisticated framework will generate unfavorable results. To validate the effectiveness of the invariant-based anomaly detection framework, the authors conducted experiments on two real-world ICS testbeds, WADI or WADI and SWAT or SWAT, both designed to emulate actual water infrastructure systems. Starting with WADI, the water distribution testbed, this setup simulates the flow of treated water through a multi-stage distribution system. Data was collected at a frequency of 1 Hz over 16 days, with the first 14 days being normal system operation and attacks being launched during the last 2 days. During these 2 final days, 15 targeted attacks were launched. The types of these attacks varied, ranging from overflow and contamination events to stealthy manipulation of sensor set points. The system was trained on 12 days of data that contained only normal operations, ensuring that the model had no prior exposure to attack scenarios. I've included a table from the paper on the right. This table summarizes the attacks that the researchers launched against the WADI testbed. You can see that there's a mix of physical process manipulations and subtle disruptions, such as pipe bursts, raw water conductivity changes, and chemical injection. This variety helps demonstrate the framework's ability to detect both overt and covert anomalies, which is a key requirement in real-world industrial control systems. Next, the SWAT testbed, which is the Secure Water Treatment System, focuses more on the treatment phase rather than distribution. In this setup, researchers injected 36 distinct attacks over the course of 4 days. Training was done using 5 days of data from normal system operations. These attacks targeted valves, chemical dosing, flow control, and even attempted to cause stealthy overflows. Overall, these testbeds provide a realistic and rigorous environment for evaluation, closely mirroring the complexity and constraints found in actual critical infrastructure. On this slide, we'll look at the core evaluation results that demonstrate how well the proposed framework performs in detecting anomalies in industrial control systems. The data sets that were evaluated were generated from the WADI and SWOT testing that we previously discussed. Across both data sets, the system achieved high precision and recall, meaning it correctly flagged most anomalies while minimizing false alarms. This is essential in a live ICS environment where both misdetections and false positives can lead to costly or dangerous outcomes. I've included a table from the paper showing the performance metrics of 3 detection models tested during the WADI case study. The first of these models is design-based invariant rules, which are essentially manually engineered rules. The second model tested is the residual error-based model, which is a typical statistical baseline as it is used more typically across the industry. And finally, the results for data-driven invariant rules are listed. In this table, we will focus on 3 key metrics: TPR, or true positive rate, FPR, or false positive rate, and NTPR, or normalized TPR. One of the most important comparisons here is with baseline residual error-based models, which are used more traditionally. These models estimate what a sensor value should be and flag deviations. However, they often struggle in multivariable systems because they lack structural context. If you look at the true positive rate and normalized true positive rate, you will find that the data-driven model leads or matches the other 2 models. In the P1, P3, and P5 metrics, which tell us how well the system ranks true anomalies at the top, the data-driven approach scored a perfect 15 out of 15. It also keeps the false positive rate very low, which is on par with the residual model. This is crucial because a system that generates too many false positives will be likely ignored by operators. Overall, these results show that this framework doesn't simply detect more attacks, but it does so in a way that is scalable, interpretable, and usable in production environments. One of the most compelling strengths of this framework is that it automatically generates invariant rules from operational data, something that has traditionally required a lot of manual engineering. In older systems, experts had to define normal operating rules by hand, which was not only time-consuming, but also prone to human error and limited to their existing knowledge of the system. The automation provided here changes that dynamic. It enables scalability. Once the system is deployed in one environment, it can be reused or retrained for other ICS networks without starting from scratch. This makes it practical for wide-scale adoption across industries like oil and gas, electric grids, or manufacturing. Another major advantage is that the rules generated are interpretable. These aren't black box alerts. They are logical if-then statements that a control engineer can read, understand, and validate. This transparency is essential for operator trust and makes incident triage much faster. The framework also adapts to change. Since rules are derived from normal historical data, if system configurations or workflows evolve, you can retrain the model with updated logs to produce new valid invariants. That helps future-proof the system against drift. And importantly, unlike some model-based or physics-based approaches, this technique doesn't require a detailed prior process model. It learns purely from observation, which lowers the barrier to deployment. All of these features combined support an overarching goal: to detect threats early, reliably, and in a way that's actionable in the real world. Of course, no system is perfect. One limitation of this model is the need for clean training data, as it assumes that the logs used for training represent normal system behavior. If those logs contain undetected anomalies, the system may treat them as normal behaviors. Additionally, while this approach is strong against many kinds of attacks, it can still be vulnerable to carefully crafted, stealthy adversarial behavior if it mimics normal signal patterns. The authors mention several promising directions for future work, including online or continuous learning models, lightweight versions for edge deployment, and combining this technique with others like physical model-based detection or signature-based alerting. To wrap up, this research presents a systematic and data-driven framework for detecting anomalies in industrial control systems by learning from their own operational history. Instead of relying on predefined physics-based models or handcrafted rules, this framework automatically discovers invariant relationships that should always hold true during normal operations. These invariants are used to define logical rules that can detect when something in the system deviates in a meaningful way. One of the core innovations is that the framework is fully data-driven. It requires no prior process model and no manual rule creation, which significantly reduces the deployment barrier, particularly in large, complex ICS environments. The authors tested this framework on two real-world testbeds, being WADI and SWAT. Both are realistic water infrastructure systems, and both include dozens of sensors, actuators, and control logic. The results showed that the framework achieved high detection accuracy, low false positive rate, and consistently ranked real attacks at the top of its alerts. Equally important is that the output of the system, the invariant rules, are human readable and interpretable. This means that ICS operators and engineers can understand what triggered an alert, which makes adoption in live environments far more practical. The framework is also domain agnostic. While this paper focuses on water treatment and distribution, the approach is general enough to be applied to power generation and transmission systems, oil and gas, or manufacturing networks with minimal adjustments. So, in summary, this approach represents a promising step forward in ICS security. It is accurate, efficient, explainable, and scalable, which are exactly the characteristics that I believe we need in modern industrial cybersecurity solutions. Thank you very much for your time and attention. I look forward to discussing this incredibly interesting framework with you all in Ed Discussion.